In electromagnetism, charge density is a measure of electric charge per unit volume of space, in 1, 2 or 3 dimensions. More specifically, the linear, surface, or volume charge density is the amount of electric charge per unit length, surface area, or volume, respectively. The respective SI units are cm-1, cm-2 or cm-3. Like any density, charge density can depend on position, but charge and thus charge density can be negative. It should not be confused with the charge carrier density, the number of charge carriers in a material per unit volume, not including the actual charge on the carriers in chemistry. It can refer to the charge distribution over the volume of a particle, such as a molecule, atom or ion. Therefore, a lithium cation will carry a higher charge density than a sodium cation due to the lithium cations having a smaller ionic radius, even though sodium has more protons than lithium. Definitions. Continuous charges following are the definitions for continuous charge distributions. The linear charge density is the ratio of an infinitesimal electric charge dq to an infinitesimal line element. Similarly, the surface charge density uses a surface area element ds and the volume charge density uses a volume element dv. Integrating the definitions gives the total charge q of a region according to line integral of the linear charge density lambda q over a line or 1D curve C. Similarly, a surface integral of the surface charge density sigma q over a surface S, and a volume integral of the volume charge density rho q over a volume 5, where the subscript q is to clarify that the density is for electric charge, not other densities like mass density, number density, probability density, and prevent conflict with the many other uses of lambda, sigma, rho in electromagnetism for wavelength, electrical resistivity and conductivity. Within the context of electromagnetism, the subscripts are usually dropped for simplicity. Lambda, sigma. Other notations may include rho, rho-s, rho-v, rho-l, rho-s, rho-v, etc. Average charge densities. The total charge divided by the length, surface area, or volume will be the average charge densities. Free, bound and total charge. In dielectric materials, the total charge of an object can separate into free and bound charges. Bound charges set up electric dipoles in response to an applied electric field E, and polarize other nearby dipoles tending to line them up. The net accumulation of charge from the orientation of the dipoles is the bound charge. They are called bound because they cannot be removed. In the dielectric material, the charges are the electrons bound to the nuclei. Free charges are the excess charges which can move into electrostatic equilibrium, i.e., when the charges are not moving and the resultant electric field is independent of time, or constitute electric currents. Total charge densities in terms of volume charge as densities. The total charge density is, as for surface charge densities, where subscripts F and B denote free and bound, respectively. Bound charge. The bound surface charge is the charge piled up at the surface of the dielectric, given by the dipole moment perpendicular to the surface, where S is the separation between the point charges constituting the dipole. Taking infinitesimals and dividing by the differential surface element ds gives the bound surface charge density, where P is the polarization density, i.e., density of electric dipole moments within the material, and dV is the differential volume element. Using the divergence theorem, the bound volume charge density within the material is hence. The negative sign arises due to the opposite signs on the charges in the dipoles. One end is within the volume of the object, the other at the surface. A more rigorous derivation is given below. Free charge density. The free charge density serves as a useful simplification in Gauss's law for electricity. The volume integral of it is the free charge enclosed in a charged object, equal to the net flux of the electric displacement field D emerging from the object. See Maxwell's equations and constitutive relation for more details. Homogeneous charge density. For the special case of a homogeneous charge density ρ0, independent of position, i.e., constant throughout the region of the material, the equation simplifies to. The proof of this is immediate. Start with the definition of the charge of any volume. Then, by definition of homogeneity, ρq is a constant denoted by ρq, 0, and so by the properties of an integral can be pulled outside of the integral resulting in. So, the equivalent proofs for linear charge density and surface charge density follow the same arguments as above. Discrete charges. For a single-point charge q at position r0 inside a region of 3D space R, like an electron, the volume charge density can be expressed by the Dirac delta function, where R is the position to calculate the charge. As always, the integral of the charge density over a region of space is the charge contained in that region. The delta function has the shifting property for any function f. So the delta function ensures that when the charge density is integrated over R, the total charge in R is Q. This can be extended to n discrete point-like charge carriers. The charge density of the system at a point R is a sum of the charge densities for each charge chi at position r, where I equals 1, 2. The delta function for each charge chi in the sum, delta, ensures the integral of charge density over R returns the total charge in R. If all charge carriers have the same charge q, the charge density can be expressed through the number of charge carriers per unit volume. N. By similar equations are used for the linear and surface charge densities. Charge density and special relativity. In special relativity, the length of a segment of wire depends on velocity of observer because of length contraction. So charge density will also depend on velocity. Anthony French has described how the magnetic field force of a current-bearing wire arises from this relative charge density. He used a Minkowski diagram to show how a neutral current-bearing wire appears to carry a net charge density as observed in a moving frame. When a charge density is measured in a moving frame of reference, it is called proper charge density. It turns out the charge density ρ and current density J transform together as a four-current vector under Lorentz transformations. Charge density in quantum mechanics. In quantum mechanics, charge density ρq is related to wave function psi by the equation where q is the charge of the particle and psi2 equals psi asterisk psi is the probability density function, i.e., probability per unit volume of a particle located at R. When the wave function is normalized, the average charge in the region RR is where d3R is the integration measure over 3D position space. Application. The charge density appears in the continuity equation for electric current, also in Maxwell's equations. It is the principal source term of the electromagnetic field. When the charge distribution moves, this corresponds to a current density.